and welcome to another WJEC A level physics question. This time is question 3 from January 2014, Unit 1, and it's an equations of motion type question. Starts off with a velocity time graph given for a body which is accelerating from rest in a straight line, and we're asked first of all what the shaded area under the graph represents. Well, because this is a velocity time graph, that area represents displacement. Can't really get away with distance because that would need to be a speed time graph. Next we're asked to show, using the graph and the usual symbols, that x equals a half at squared. Well, x is the displacement anyway, so x is the area under the line. The area under the line is simply a triangle, and the area of a triangle is half base times height. So it's half of t for the base times v for the height. But also we have that the gradient is the acceleration. So the gradient is v minus u generally over t, but here u is 0, so we can say that the acceleration is simply v over t, and hence v is a times t. So if we go back to the previous expression, if we replace the v by a times t, you'll see that we get the half at squared as required. Next we're told that a ball is thrown vertically upwards and passes a window ledge 0.3 seconds after being released, and it passes the window ledge on its way back down 1.6 seconds later, and ignore air resistance. We're going to determine the time of flight of the ball. Now the key point here is, because we're ignoring air resistance, the flight of the ball will be symmetrical. It will take the same amount of time to go upwards as it does to go downwards. So in terms of the diagram, the first 0.3 seconds up to the ledge, then we've got 1.6 seconds in total from the ledge to the maximum height and back to the ledge again. We'll have another 0.3 seconds to fall from the bottom of the window ledge down to the ground, and if we add all those times together we'll get 2.2 seconds. Next we're asked to calculate the initial velocity of the ball when it's released. So we need to set this question up carefully. So what we're going to do is, first of all, be very clear in our minds what part of the motion we're going to look at. Here I'm going to look at the motion from the ground up to the maximum height. You could look at the ground all the way back to the ground again. You still will get the same answer by doing a very similar sort of calculation. Next we choose a direction to be positive, and if we're initially moving upwards, taking upwards as positive is often a good idea. Then we can fill in the 5 letters of the Suvat equations as are often known, though WJEC doesn't use S anymore, uses X for displacement. So let's fill in what we're trying to find. Well, u is the unknown, so I'm going to just put a question mark next to u. X is another unknown, but I'm not actually interested in this part of the question. The acceleration is going to be minus 9.81 meters per second squared. It's negative because we defined upwards as positive, and the acceleration due to gravity acts downwards. If we're looking at ground to the maximum height, then the time of that part of the flight will be half of the total time. So it's 1.1 seconds, not 2.2 seconds that I've seen people try before. This is why we need to be clear in our minds what part of the motion we're looking at. And similarly, if we're looking at the ground to the maximum height, at the maximum height, the final velocity, just for an instant, is 0 meters per second. If you wanted to consider the entire motion here, then we could change things around where v would be the negative of u. It would be the same speed that it left the ground as it hits the ground, but in the opposite direction. And then the time of flight would be 2.2 seconds. Anyway, we're going to use the equation without x, and that equation without x is probably the easiest of them. Simply v equals u plus at. So let's rearrange this for u. U will be equal to v minus at. V is 0, then we've got minus 9.81 times 1.1 seconds. So that will give us 10.8 meters per second. And note this is a positive value because obviously the ball is moving upwards initially. For the next part of the question, we're asked to calculate the height of the window ledge above the ground. So again, it's really important to be clear of exactly what part of the motion we're looking at. So we're going to be looking at the motion from the ground to the ledge. We're still going to take upwards as positive. Let's have a look what we can put in for our letters. Well, the time to the ledge was 0.3 seconds. That was given to us in the question at the start. The acceleration is still minus 9.81 meters per second squared. X is what we're trying to find. U is the 10.8 meters per second that we worked out in the previous part of the question. And V is an unknown that we're not actually interested in for this part of the question. The equation without V is x equals ut plus a half at squared. So let's carefully put in the figures. 10.8 times t, which was 0.3 seconds, plus a half times minus 9.81 times 0.3 squared. And if we put those into the calculator, we'll get 2.80 meters. 2.8 meters will be fine. Now for the next part of the question, we were asked to draw on the grid below a velocity time graph for the whole of the ball's flight and include suitable scales on both axes. So I've pre-drawn this. I've decided to use a vertical scale where the major axes are separated at 4 meter per second intervals. You could possibly use 5s on these points if you liked. It's entirely up to you. Now the initial velocity was a positive 10.8 meters per second. After 1.1 seconds, the ball is at the top of its flight where its velocity is 0. And after 2.2 seconds, the ball is moving downwards, just about to hit the ground at a velocity of minus 10.8 meters per second here. Axes were already labelled for you, so all we had to do was plot the points and join them up with a perfect straight line. Remember that the gradient of this straight line represents the acceleration, and if we actually calculated it, we would find it was 9.81 or minus 9.81 meters per second squared. For the next part of the question, the last part of the question, we're told that in reality air resistance also acts on the ball, and we've got to draw 3 free body diagrams showing the forces acting on the ball at the positions indicated, and we've got to label the forces. Well, one force that doesn't change no matter what position we're in is the weight of the ball. So I'm going to draw an arrow, I'm going to label it as W, and I'm going to draw same size arrow on each diagram. I'm going to put a little key by the side. The W is the weight, so rather than labeling on every single diagram, just going to use that key. In the left hand diagram, as the ball is moving upwards, air resistance will be in the opposite direction to it, so we need a downward arrow here. So for example, I could draw that arrow there, or I could draw it underneath the ball, label it how I like, and I'm going to put a key that R is my air resistance force. In the middle diagram, when the ball's at the top of its flight, it's not actually moving for that instant, and therefore there's no air resistance force. Remember, air resistance is caused by collisions of air molecules with the object. If the object's not moving, effectively we can forget about the collisions with the air molecules. So the middle diagram is complete. In the final diagram, if the ball is moving downwards, then the resistive force will be upwards. So I'm going to draw an upward arrow and label it as R. And technically the two R's would be the same length, because the size of the velocity of the ball in both positions when it passes the window ledge will be equal, but obviously in opposite directions there. And similarly, the weight is the same size in each diagram. Thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments below. Goodbye.